Welcome to lesson 13, seismic hazards. So we've moved off the volcanic hazards section where we looked at the causation, distribution, frequency, magnitude, the different sorts of impacts, and the case studies, and the management aspect of it. This one, so we're moving on to a new section, kind of follows a similar format, but instead of volcanicity, we're now dealing with seismicity, so the study of earthquakes. So this just simply symbolic where we've got two plates sliding past each other. And I'll say this quite regularly throughout this one here. You get earthquakes at all plate boundaries. And if I do forget, I wasn't directly dealing with it here, but you also get what we call I-N-T-R-A, intraplate earthquakes as well, where they fall in between plate boundaries, probably some sort of ancient fault line or possibly even linking that to human cause, where an earthquake can take place hundreds, maybe even thousands of kilometers away from a plate boundary. Just the overview here, so we can see here, very much here, setting the scenes of plate tectonics. So we've already talked about earthquakes many times already. We look at the hazard itself, the causes of the key terms that come with it, and look at the actual hazards that come within this. I think pretty much most of this stuff we'll cover today. So in today's session, I'll look at the definition of it, distribution of it, that type of thing, the earthquakes at different plate boundaries, the basic explanation, move into shockwaves. Don't want to get too obsessed by that, but just to make sure we covered it. And also then look at the primary and secondary hazards that come with this. This won't be about the case study, won't be about the measurement of it. And did I say management? I think I said management. And certainly won't be the case study. So there's a series of lessons. If you remember when we did volcanoes, there's quite a few sessions to do with that. Okay, right, let's move on. Now I'm not going to click on this site. This is the US Geological Survey site. So if you, I've got obviously the PowerPoint of this, and I've got a document that goes with this, and you can click on it, and it takes you to a world map, and you can zone in, zone out. It's free, and it looks at all the earthquakes that have happened within the last 24 hours over a certain size, magnitude. I think it's 2.5. So literally thousands of earthquakes go off every day, and they're not. You don't feel them, register them, A, because they're too small or they're too far away. But they're quite interesting, and they use proportional circles. It's a good example of geographical information systems. That's a word you need to be familiar with. And I suppose it's geospatial data as well. Two words that throw students quite a lot in this course. Okay, so again, every opportunity there is to repeat some of these words, it gets it into your vocabulary, your literacy. This, if you get a chance, click on this one. Again, I'm not going to do this in this video. This actually shows the Kobe earthquake of 1995. 4 or 5,000 people were killed, and it shows, up to 40 seconds of, not this particular video, but it actually shows some people inside a building and shows the shockwaves and how they're moving about in the building. Outside, it was absolutely carnage. Okay, so just a nice little video to look at, just to get a sense of what's going on. You won't get a question that says, what are earthquakes? It will be about the causation. It'd be something much more specific. And ultimately, it's ground shaking for whatever reason that might be. So if I just bring this up here, if you do look it up in a variety of dictionaries, ultimately it's the sudden violent movement, the breaking, the fracturing of the earth below us, and followed by a series of shock waves resulting from that movement, that fractured breaking. It's come from the Oxford Dictionary. Okay, but you're not going to get that, but you should know something about that. Very interesting map here. All the red dots are like the positions of many of the big earthquakes from the past, and it's created up a pattern here. And I think many of you will recognize and remember that, for example, is the Mid-Atlantic Ridge. This here is a conservative boundary over here, where they're sliding past each other in different directions, by the way. And you have the world famous San Andreas fault line, over 1,000 kilometers long, but there are literally hundreds of fault lines along here. And we have the subduction zone over here. We have the collision zone over here. But also you'll see that the world has got dotted lots of red dots as in representing the earthquakes, which are a considerable distance away from the plate boundaries. And again, to repeat that word intra, that means within, um, intra plate earthquakes, so not near the plate boundaries. This, what's coming up, I don't know if you can see this. This is just like when you're describing it, certain words that you need to be able to use. This is particularly useful on the 6-mark analysis questions where you're describing. So linear, if I do this, and it's not a line as in straight line, but you can see it's quite narrow, thin, and it follows the pattern of the plate boundary there, so relatively narrow, that linear. And then this one over here, stuck on its own, outlier, anomaly. And then the final one coming in here is a cluster where you see a big grouping of them together, sometimes called, yeah, like a clustered effect, nucleated, compact, that side of it. And remember, your descriptions are important, not basic descriptions. And this is a very pattern orientated resource that you see in front of you. So knowing your continents, like Africa, for instance, or South America, knowing that's the west side, the east side, your names of your oceans, they can be very, very useful in adding extra layers of depth, getting you into level 2 because you can describe the pattern a bit more clearly. Anyway, let's move on. This one is just simply some of the big earthquakes that have happened in the past. A bit outdated, this map actually, because it's been superseded. There's been stuff in Japan more recently. We obviously got Turkey last year in 2023. Um, It's got the Shez one. No, it hasn't got the Shez one. Shez one was one of the biggest ones in mainland Asia. That's not on there. But it's just to give you a little bit more of something a bit more to focus on. So coming on to just some general descriptions here. So as you've seen, we've got very strong association with plate boundaries where they meet. You get earthquakes potentially at all plate boundaries. And sorry, the thing just paused there a bit, so I won't start again. I'll just repeat it here. And ultimately, the key fundamental cause of earthquakes is that the rock, the plates, the crust is trying to move, and we're getting friction because it's not lubricated, and you've got like opposing forces taking place, and that creates it sticks. So when something tries to move against each other, if it doesn't slide past it easily, then it will jam, jolt, not jolt, it will lock up. I'll go into that a bit more sort of depth in a moment. Now here, and just to repeat, we get earthquakes at all plate boundaries. This one, let's see if you can remember which type of plate boundary this is. Ocean plate going beneath the continental plate. We've got subduction. So that's a convergent boundary or a destructive boundary. This one here, we have the conservative. Now, actually, this looks like it's the off the American coastline, but it's actually a cartoon picture. Um, in this instance, this conservative plate boundary, they're moving in different directions. So again, you can see how as they slide past each other, they jam up. I think we need to also remember here, the forces here are unimaginably big, right? And we're talking about rust that's so deep, the rock structure is it's not like some sort of cartoon or some blocks that you just slide past each other. That's a conservative. You definitely get them at these two. And in fact, the magnitude, the size of earthquakes tends to be really big at these two here. So the destructive and the conservative. Now, it doesn't say that here, but you do get them at constructive where they move apart, and you do get them at collision zones as well. But these are the worst two. I simply have this picture on here. It's like a ripple. It's not actually, clearly it's not an earthquake. It's like when you drop a pebble in the pond, the ripple moves outwards. And if you look here, the ripple's strongest here. And as we move away, as this wave that's been created, it dissipates in terms of size. And that's a similar sort of process that's happening with earthquakes. The energy goes across the surface, through the crust, through the mantle, and can be registered in other parts of the world. And remember one of the first few lessons, earthquakes are a really good way of helping us to understand the interior of the Earth. It's obviously a collection of data, bits of evidence, extrapolation, things like that can get us to come to that conclusions. But earthquakes are going off every day and they're registered. Now, I've included this one on here. This isn't really for an activity to do now, but you'll notice there's some key words here: focus, fault line, epicenter, seismic waves. And as I go through the next picture, I'll put some of these things into perspective. Then here we've got the cartoon setup. So this is our crust. This is the fault line where two plates meet and they're attempting to move. And so this could, in this instance, I mean, I suppose technically speaking, that could be subducting. I think the way this one is probably working, this diagram, is one plate is moving that direction, this plate's moving this direction, or in the same direction at different speeds. We've got the plates locking up here. The point at which the rock breaks within the crust is known as the focus, and you'll see that now. So that's a word that you need to be aware of. And that break point can trigger close to the surface, or it can be really deep down. Kind of, I'll talk more about that later on. In fact, I did talk about it with when I did the destructive plate boundaries. So the shallow focus is nearer the surface. I said that you have intermediate, we already talk about those, and deep focus earthquakes. And usually the shallow focus earthquakes are worse because more of the energy is felt at the surface. Now, directly above that, you see another arrow coming in. Directly above that, we call it the epicenter, and that's where the shock waves are the strongest. And it might be that's where the most amount of damage might take place. But it depends. It depends on the level of development, depends on the geology. There's a whole other bunch of factors that come into play, right? So that's something that you have to think about in determining the severity of an earthquake event. Here, that's the fault line. That's where the two plates meet, and it's rarely just like one sharp edge, as I say in California. There's several, well, more than several. There's quite a lot of fault lines that run up and down California. And then these red dotted lines radiating out, a bit like that ripple that I mentioned in there, the seismic waves. So that's the energy that goes out. And it's strongest here. The magnitudes are strongest here. In the next video, I'll talk about how we measure um, these earthquake events. We use there's I think three that I'll go through. You've got the Mercalli scale, you've got the Richter scale, and then you've got the magnitude scale, and I'll make that really, really clear. So I would say there are some shared fundamentals here that you can adapt for each of the plate boundary types. But fundamentally, what we're saying here, they happen along the boundaries of the plates. Now, what we're saying here, and I haven't said it here, you could say that the plates either move apart, they move together, or they move past each other. And that's driven, you could say, by the convection cell in the mantle. So the plates come together. As they move past each other, friction takes place and they try to move, and then they lock, they freeze up, not freeze cold, but they lock up. Now that locking, there's energy building up because they're still attempting to move, and it's got like it's getting a lot of stored energy, and then over a period of time, this can run into hundreds, thousands, tens of thousands, in fact, even millions of years, where you get this pressure build up, and eventually it comes to a point where there's a slip, there's a jolt, there's a jerk, and there's a sudden release of energy. And that energy happens at that fault line. We call that the focus. Huge energy goes out, seismic waves. And I've already mentioned about the epicenter. So it's well worth practicing that because you get that with subduction, you get that the conservative, you get the constructive, and to some extent with the collision zone. So it's kind of shared fundamentals there, well worth learning that. On this slide, what I've done is like this is how I would learn this. And I just put some of the key words here, and I learn that order. There's less volume of words to learn, and they act as triggers. So I trust myself that I understand this well enough that I could turn these into sentence. So I think, if again, just repeating myself, the convection currents in the mantle move the plates. And then talk about how if I said subduction, motion going under continental, as they attempt to move towards each other or past each other, it creates friction. Plates lock together, builds up tension or pressure. Eventually, there comes a break point. There's a slip, jolt, as I said, and I would go, oh yeah, I need to mention the focus. Do that, and then we have this energy released seismic waves. Okay. Now, on this bit here, this is where I go into much more, it's not nuanced stuff, but it's just more specific, a little bit more detailed. So, just a few things here, and I'll go through the gist of it because I'm a bit worried I don't want to make the video too long. So this one here was saying that you get them at constructive margins, e.g. the Mid-Atlantic Ridge. The frequency is probably less common and the magnitude is not often very strong. And if I just summarize this into a few key ideas, you can do a little bit more of the intense reading here. We're saying is that the tensional force doesn't build up as much. And remember that the plate here is relatively new and it's relatively weak, partly because of its newness, maybe hasn't solidified enough, but also the physical makeup of the crust. And therefore, you don't get the same tensional forces building up. Remember, you get these right angle fault lines to the ridge. That's probably where you're going to get most of the earthquakes taking place. And there's just some examples. So yes, constructed, but there's just a little bit of explanation about why they tend to be less on the magnitude scale. Now, conservative, this is to say they either slide past each other or slide in the same direction but at differential speeds. Here, the earthquakes tend to be relatively shallow. That means they're quite close to the surface. 5-10 kilometers would be shallow. And the tensional forces here can be quite extreme. But because they're shallow, more of the energy is released on the surface. So it has the potential to be quite severe. And the famous example of this is the San Andreas fault. There, and if you read that through again, we've got this friction building up, tension, locking, all those sorts of things that I've mentioned before. And if you talk to Californians, they're always living with the risk of the big one, supposedly. I mean, not supposedly, it will happen some point in the future. Very difficult to predict where that would be because obviously these fault lines are really long, very difficult to measure. Then we come on to the subduction zone. And here you can see these different colors. This is the Benioff zone. Remember, that's the friction zone. And these here would be shallow. That would be intermediate. And that would be deep focus earthquakes. So again, the tensional forces here can be quite severe. I would say, again, these ones here, because they're shallow, going to cause the highest magnitude ones. And again, it's just a rinse repeat in terms of the explanation. And again, the writing just supports that. But here they can be really severe. So remember, conservative and destructive margins. For some reason, I've written down subductions margins. I don't know why I did that, but it is subducting. But I am talking about destructive margins at the risk of confusing you. Then we have the collision zone. If you remember the collision zone, two continental plates moving towards each other, and what you've got here is where you've got ocean sediment pushed up, and that can create some tensional force there, and you do get earthquakes, and occasionally they can be quite severe. And there was that, if you look down here, the Shazwan earthquake in 2008 was really, really bad. I think it was close to 100,000 people being killed. All right. Okay. So again, just to sum up on that. So far in the video, I've gone through some key terms. I've gone through the key causation of it. I've talked about saying that you get them at all plate boundaries. And then I've just given you a little bit more specific knowledge, understanding hopefully about which types of plate boundaries they're worse at, and also just to remind you, I talked about intraplate earthquakes. So just a little bit on this, because this is mentioned, shock waves. And I say I don't want to get too bogged down on this. So the sorts of shock waves that are given off. So you get what we call body waves and you get surface waves. So I'll start with body waves first of all. Primary and secondary. The primary waves travel through the crust, the solids, and liquid as well. They can travel through that. They're the fastest. And the secondary waves also are the body waves, but they can't travel through liquids. Okay. In fact, it's well, I'll come on to the next bit here. So they're the body waves. So if we look at the surface waves, we have Love waves and Rayleigh waves. So L and R, just for shortening there. They travel along the surface, and these are the ones that tend to cause the most damage, right? So, and on the next slides, we'll go through the basic movements of that one there. And again, you don't need to get too bogged down in the details here because it gets a little bit, can get a little bit complicated. in terms of depth, and we don't need that. I think we just need to have a very basic understanding of this. So four waves, you've got the body waves and you've got the surface waves, and but these two here are the ones that cause the most damage. Okay, so talking about the body wave here. So this is the fastest. What happens here? We've got, like, if you look here, compression and dilation, so squeezing and extension. And so the shock waves are going back, the rock is effectively going backwards and forwards, and that will cause movement. But the fastest and of the, I suppose, of the four probably causes the least amount of damage. Going on to the secondary wave, here, this is where it effectively kind of like it's, if it's a person that's swaggering side to side, and the second fastest here. Okay, so this is more just an awareness of the wave itself. Just a visual representation. I'm not sure that really represents it, how I would do it, but that's what came up when I was looking at these things here. So again, don't get too got bogged down with this here. Again, this one here, backwards and forwards, compression, dilation. And what we're saying here, this is like going side to side. And I don't think that picture really demonstrates it very well. Depends on your, I suppose, the angle in which you're looking at that picture. Moving back to the surface waves here, these are the ones that tend to cause the most damage. Um, and let's just have a quick reminder here. Where have I got it here? Yeah, so effectively what's happening here, the love wave or the long waves, is that they're kind of the rocks going up and down, as you can see here, and it creates tremendous amounts of damage. It's like a Mexican wave type sort of effect. So again, very, very damaging. And the Rayleigh wave, or Riley wave, sorry, is kind of a version of that. And again, it's like rolling waves on the ocean, and the wave vertically and horizontally as well. So in the direction they're traveling. So these two waves here, the ones that um, they cause the most damage, they're slower than the waves that we talked about on the body waves. Okay, so again, just to have that basic element of it, and remember there will be the PowerPoint of this, so you can do it in a more measured way. You know, if you want to go into more depth, and it's well documented. Okay, so there we go. They're the two waves. Top one is the Rayleigh wave, and the lower one is the Love waves. Now, the final section that I'm final section here that I'm looking at the impacts. So again, it's important that you understand the impacts, just like with volcanic impacts. So the key things here that we're saying, like the primary physical impact of an earthquake is the ground shaking. And then therefore buildings collapsing, buildings being damaged, destroyed, roads, railways, airports, you name it, that would be primary. And if you look here, ground rupture, that's where the ground actually breaks, and you know, you can see part of the rock underneath it, but it breaks up the infrastructure above it. So people dying from being buried, crushed, things like that, or injured, that would definitely be your primary effects or impacts, depending which words you want to use. Now, on the secondary impact, this, by the way, came up as a question a couple of years ago, liquefaction. And you can see the gentleman here demonstrating it, where he's shaking the container. I don't know if it's sand or what he's got in there. And he's got water in there, and as he shakes it, it actually hasn't come out that well this time here, but you do notice it. What happens, you notice the container inside is sinking. So what happens is this is a secondary impact. In certain situations, you have ground which is unconsolidated, that means loose, porous, there's a water table in it, and as the earthquake takes place, the energy reverberates around that particular area. It might be in like a basin, and what happens is it causes the water to rise up grounds off through the pore spaces, and it destabilizes it, and it effectively acts a bit like quicksand. And if you've got building infrastructure that's not set up for that, you know, like it's not sitting in a tray or something like that, it can sink, and you can see buildings falling down. This picture here that you see, this I think is from the Christchurch earthquake, where these cars have sunk in, and then after the event, it re-solidifies, and they're like jammed in there. You almost, I suppose, in a way, it would be cool to keep it, because it's a pretty crazy photograph, I think, and very much a secondary impact. Earthquakes can cause landslides and avalanches. Okay, so they trigger because there's ground movement. Tsunamis, which that's for another lesson to go in any sort of depth. So like volcanoes, they can create giant waves. And this is where and I won't go into it in huge depth here, but this is where if you have a fault line in the sea, in the ocean, on the sea floor, where you get like upthrust from like plate movement, and it pushes the water up, and then it goes out to the sides, creating these huge waves that can travel as fast as a commercial jet. But that's ultimately what that's about there. So that's the end of the video. Just to repeat what this has gone through. I tried to keep it under half an hour, this one. So I've gone through what are earthquakes, causes of earthquakes, linking to the different plate boundaries, saying which ones tend to be worse and why. Talked about the shock waves, the primary, the secondary waves, the love waves, and the Rayleigh waves, and then finishing by looking at the primary effects and the secondary effects. Okay, so next lesson, what I'll do is I'll go through how we measure earthquakes. Okay, thanks for listening. See you next lesson.